Hello, everyone. Welcome to this lecture on transformations and the delta method. So in this lecture, I'm going to discuss two main topics, transformations. Here we will discuss how to find out the distribution of a transformation of a continuous random variable. And then the second topic is delta method. This is mainly used to get an approximation for the variance of a random variable. So these are the two topics that will be discussed in this lecture. Okay, so let us look at the first one, distribution of transformations. Right. So suppose x is a continuous random variable with cumulative distribution function capital F subscript x and the probability density function simple f subscript x. Suppose that random variable y is obtained from x through the transformation y is equal to g of x. Our objective is to determine the distribution function, that is CDF, and the density function of the transformed random variable y. So for this, there's a well-known theorem that we can use. So let me read out the theorem first. Suppose x is a continuous random variable with probability density function f subscript capital X. Set capital A to be the support of fx. That is the set of x values where the fx is greater than 0. Assume that y is equal to gx defines a one-to-one continuous transformation of A onto B. So we are considering one-to-one transformation, continuous transformation. The second condition is the derivative of x equal to g inverse y with respect to y is continuous and non-zero for y values in the set B. If these two conditions are satisfied, then y is equal to g of capital X is a continuous random variable with a density function given by the formula here. F of y evaluated at simple y is equal to f of x evaluated at g inverse y times the absolute value of the derivative of x with respect to y when simple y is in the set capital B. So this is the theorem. It's a very useful theorem that we can use to derive the density function and also the cumulative distribution function of a transformation, one-to-one transformation y is equal to g of capital X. So we are able to derive the density function or the CDF of y in terms of the density function over the CDF of x. That's very useful. So to prove this, let us consider the proof in two parts because a one-to-one transformation is either monotonically increasing or monotonically decreasing. Right? A one-to-one transformation cannot be both at the same time, but either it is monotonically increasing or monotonically decreasing. So let's consider these two cases separately. So suppose G is monotonically increasing at the first part. Then we know that dy by dx is greater than 0 if it is monotonically increasing. And similarly, dx by dy also greater than 0. Now let us derive the cumulative distribution function of y, capital Y first, and then from that we can get the density function of y. So by definition, the cumulative distribution function of capital Y, denoted by f subscript capital Y, evaluated at a simple value y real, is equal to the probability capital Y, the random variable, less than or equal to this real number simple y. That is coming from the definition of the cumulative distribution function. This definition is actually correct for a discrete random variable or a continuous random variable, both. But here we are considering a continuous random variable. So now we can write down this random variable y in terms of the transformation, because we know that y is equal to g of capital X. So just replace y by g of x. So we get this expression. Now, because g is a monotonically increasing function, it is something like this, going up, right? Monotonically increasing. So therefore, if gx less than or equal to some y, so gx, if I consider this to be g of x, g of x is less than or equal to some value y, that is this area, when x is less than or equal to g inverse of y. If this is y, then this will be g inverse y. So you can see that gx is less than or equal to y, that is this curve here, when x is less than or equal to g inverse y. That happens when g is monotonically increasing. So we can get this expression. But now notice that the probability random variable x less than or equal to this real number is by definition is the cumulative distribution function of capital X, that is a random variable, evaluated at this real number g inverse y. So therefore, we can very easily get an expression for the cumulative distribution of function of y in terms of the cumulative distribution function of x. Now, if we want to get the density function of y, what we have to do is we have to differentiate the cumulative distribution function of y with respect to y here, simple y, right? So when you differentiate this, you can see this is also a cumulative distribution function. So what you get is the density function of x evaluated at this value times the derivative of this value with respect to y. You have to apply the chain rule, right? So therefore, you can see that the density function of y evaluated at y is equal to the derivative of the cumulative distribution function. So that is the derivative of this thing with respect to y. So when you differentiate the cumulative distribution function of x, you get the density function evaluated at that value of this value here. And then we have to differentiate the value inside the bracket here with respect to y. Right? So this thing is actually x g inverse y is equal to x. So this can be written as dx over dy for simplicity. Otherwise, this is what usually has to be correct, the expression, because everything has to be in terms of simple y here. But of course, we know this is dx over dy. So we can stop here or we can even go up to here. That's correct. So this is the expression that you get if g is a monotonically increasing function. Now to complete, we have to look at the other case also. That is, if what happens if g is monotonically decreasing. So now suppose g is monotonically decreasing. In that case, of course, the derivative of y with respect to x will be negative, and therefore gx by dy will also be negative. But the function will be now like this, coming down, monotonically decreasing. So in that case, again, if you apply the same argument, the cumulative distribution function of y evaluated at a real number simple y is, by definition, again, the probability y less than or equal to simple y is the same as the probability g of x less than or equal to simple y. But now, g of x less than or equal to some value simple y, that is this part of the curve, occurs when x is greater than or equal to g inverse y. So if this value is, for example, y, then this value here is g inverse y. So g of x is less than or equal to y. So that this part of the curve happens when x is greater than or equal to g inverse y. Right. But x probability x greater than or equal to g inverse y is the same as 1 minus the probability x less than or equal to g inverse y. You can still include equal sign here because these random variables are continuous. So after this, we can write down one more step if you want. That is equal to 1 minus the probability x less than or equal to g inverse y, which will be 1 minus f of x, capital F of x, that is the cumulative distribution function of x evaluated at this value. So therefore, in that case, cumulative distribution function of y evaluated at simple y is equal to 1 minus f of x, that is the cumulative distribution function of x evaluated at g inverse y. Now, in this case, in order to get the density function, again, we have to take the differentiate this function with respect to y. In that case, you will get this expression. So you have to differentiate the cumulative distribution function with respect to y. That is differentiation of this 1 minus fx with respect to y. So when you differentiate 1, of course, you get 0. Then after that, you get negative density function of x evaluated at this point times, then again, chain rule, you have to apply the chain rule. You have to take the derivative of this quantity with respect to y. So, of course, again, as previous situation, you can write down this as dx over dy. So, in that case, density function of y evaluated at y is equal to this expression. Excuse me. Right. So if you combine both cases, now in this case, notice that this quantity is negative. Dx over dy is negative, as I pointed out earlier. If the g was monotonically increasing, in that case, this is positive. So therefore, in that case, you can write down dx over dy absolute value in that case. Or otherwise, if gx is monotonically decreasing, negative dx over dy can be written as the absolute value of dx over dy. So therefore, we can write down both cases using one equation like this, right? So the density function of y evaluated at simple y is equal to f of x g inverse y times dx over dy absolute value, or the same thing you can write down as 1 over g dash of g inverse y. G dash is the derivative. But it's easy to remember, I think, if you just write down fy y is equal to fx g inverse y times the absolute value of dx over dy. That is another way to remember it. This is the expression given in the book. But I usually remember it as the density function of y evaluated at simple y is equal to f of x evaluated at g inverse y, which is actually x. Now we have to write down everything in terms of y. But then again, you can write down times the absolute value of dx over dy, in which case this term will be replaced by dx over dy. Absolutely. So therefore, that is the formula that we can use in general to find out the density function of a one-to-one transformation of a random variable x. Right. So let us look at a few examples. The first example, suppose x has a uniform distribution in the interval 0, 1, and suppose y is equal to x squared. Find the distribution of y. Now notice that when x is in this interval 0 to 1, then x square is a monotonically increasing function, strictly increasing function. Therefore, we can directly apply the theorem. So in that case, G inverse Y, which is equal to X, is equal to square root Y, right? Y is equal to X square as a random variable. Otherwise, you can write down this as simple Y is equal to simple X square. So X is equal to square root Y because now X is in 0, 1 interval. And therefore, dx over dy will be 1 over twice root y. Dx over dy is necessary for us to get the density function of y. So when you apply the formula, the density function of y evaluated at y is equal to, first of all, the density evaluated at G inverse y. But in this case, the density of x, density of f, x is just 1. Right? So therefore, that's this one. It's not going to be a function of x in that case. So it's just 1. And then multiplied by the absolute value of dx over dy. Of course, in this case, y is positive. Therefore, just you can write down 1 over 2 times square root y. When y is between 0 and when x is between 0 and 1, you can easily see that y should be also between 0 and 1. So therefore, this is the density function of y. And you can get if you are interested in the cumulative distribution function, of course, you can integrate the density function from 0 to some value y. In that case, you get capital F subscript y evaluated at simple y. So, so this is directly applying the formula. But sometimes it's easy to get the density cumulative distribution function first and then get the density function if necessary by differentiating the cumulative distribution function. So here I'm showing that method also, that path. Sometimes it is easy to derive the CDF and then to differentiate to obtain the PDF. So if you write down, get the cumulative distribution function, that's Fy evaluated at some value y, where this y is a number between 0 and 1, can be written as probability x square less than or equal to y. But it is now the probability x less than or equal to square root y, because y is between 0 and 1, the negative part doesn't come. So this is the, by definition, the probability capital X, the random variable less than or equal to some real number, is equal to the cumulative distribution function of X evaluated at that value y. But because X has a uniform distribution in 0, 1 interval, the cumulative distribution function of X is evaluated at some value X is equal to X, simple X. So therefore, the cumulative distribution function of X evaluated at root y is equal to root y. Cumulative distribution function of capital X evaluated at some value X, where X is between 0 and 1, is equal to simple X. So therefore, f of x evaluated at root y is equal to root y. So that's the cumulative distribution function. So this expression, you have to say y between 0 and 1. So if simple y is less than 0, the cumulative distribution function is 0. If simple y is greater than 1, then in that case, the cumulative distribution function is equal to 1. Right. So if you want, you can get the density function in through this thing also. This is the second part that I mentioned. So by differentiating this one with respect to y, you can get the density function that we got earlier using the formula directly.